Welcome to Data Science 1, Probability, Continuous Bivariate Example. We're going to need to know what a joint distribution is, a marginal distribution, expectation, variance, and covariance. Warning, lots of calculus ahead, so if you don't feel comfortable with calculus, you're probably not going to enjoy this video. Go back and watch the one that's on the discrete example. You'll be fine. Just don't have to stare at the calculus. But I'm going to go through it for completeness because there are lots of people who do need to know how this works from a calculus perspective. All right, so here's the formulae I'm going to use. Notice they're on the continuous case because of the integral here. I'm going to use the shortcut formulas again because otherwise it'll take too long to calculate all this stuff. So we need to be able to work with these fairly easily. We're going to use our example that we used before for our bivariate continuous case. This is one of the examples. And because we have the marginals already, and it's just going to speed everything up a little bit. All right, so you can work out the details. I didn't work them out before, but here are the marginal distributions for each of these x and y. And what we're going to go first is we're going to find the expected value of x, the expected value of y, the variance of x, variance of y, the covariance of xy, and then we're going to try to come up with the correlation. So let's start with the expected value of x. Here's our density. The expected value of x is the integral negative infinity to infinity of x times f of x dx. So here our integration limits will be from 0 to 2 because that's the support of the density. X times our density here. We're going to pull the 16 out, 1/16 out, and here we're going to push the x through. We're going to do the integration. When we do the integration here and we plug in 2 and 0, we get 68 thirds times 1/16, which is 17 twelfths, or approximately 1.416. Now, we're going to keep the answers up here so we can keep track of them. Now go to the expected value of y. Here's the marginal that we had. We're going to do the exact same process, integral from negative infinity to infinity of y times f of y dy. The integral limits go from 0 to 2 because that's the support of our density. We have 1/16, 3y squared plus 4. Next step, pull the 1/16 out. It's a constant, no need to stare at the whole time. And then we're going to push the y through. So now we have 3y cubed instead of 3y squared, and plus 4y dy because we added a y onto the 4. Oh, lost ourselves there. Okay, so now that we have this, we're going to integrate this. It comes out to this quantity here. 3y to the 4th over 4, 4y squared over 2. Going to evaluate that at 0 and 2, and it comes out at the nice number of 20. So our answer here becomes 20/16 or 5/4 or 1.25. All right, now we're off to get the variance of x. Now remember, we're going to use the shortcut formula, which means we have to calculate the expected value of x squared, and then we'll use the expected value of x along the way. Now, here we're going to use expected value of x squared. We're going to put x squared in, and we're going to do basically the same thing we did before. It's just the integral from negative infinity to infinity of x squared times f of x dx. Put in the density, pull the 16 out, push in the x squared. Notice that everything went up by the exponents went up by 2. Do the integration, evaluate it at 0 and 2, and come out with 176 over 5. And then we take that times 1/16, and it becomes 11 over 5, which is approximately 2.2. And I know you're like, okay, we're done. Well, you're not done. Okay, so here we have to use our formula, our shortcut formula. We just calculated the first piece. We've already calculated the mean from before, so it's 2.2 minus 1.416 squared, which is approximately 0.1949. Done on variance of x. Now let's move to the variance of y. Okay, now that we've got this, same general rundown, expected value of y squared. We have y squared times f of y, and then we're going to integrate it from negative infinity to infinity with respect to y. 0 to 2, that's the support on our density. Here we're going to have 1/16, and then we're going to pull it out, push the y squared through, integrate it, come out here, come up with 0 to 2, and that comes out to 448/15. Yeah, well, it takes a while to work it down, but it does. Then you multiply that by 1/16, you get 28 over 15, or approximately 1.866. Feel like you're done, but you're not done because you're using the shortcut formula. So let's go down and use the shortcut formula. We've got the first piece. We've got the second piece. We just got to steal it from up here. So we got 1.866 minus 1.25 squared, and that comes out to about 0.3035. All right, take a moment. Gather yourself together, because now we're on to the covariance. Now, the covariance is going to be a little bit different because it involves the expected value of xy, which means we're not going to work with the marginals anymore. We're going to be working directly with the joint density. So here I've got it broken down into pieces. So it's a double integral now because we have two variables, dx, dy, and then we plug in the density. We pull out the 3 over 32. I'm going to push in all of the x and y into here. So x squared becomes x cubed y. Y squared x becomes y cubed x squared by pushing that in. Then I'm going to do the integration with respect to x. This is what it comes out to. X to the fourth y over 4. Y cubed, x cubed divided by 3, evaluated at 0 and 2. When you come down here, I've just showed you plugging in the 2. The 0 doesn't matter because it's going to go away. We end up with 4y plus 8/3 y cubed, evaluated from or integrated from 0 to 2 dy with 3 30-seconds out front. Now I'm going to put in some dotted lines so that we can keep cranking here. So now that we've done that, we've got 3 30-seconds from 0 to 2, 4y 8/3 y cubed, just what we had on the last one. We're going to integrate this. This becomes 4y squared over 2 plus 8y to the fourth over 3 times 4, evaluated at 0 and 2. When you plug all this in, you end up with 56/3, and out of, then multiply that by 3 30-seconds, which becomes 7/4, or 1.75. All right. Now we feel like we're done, right? Well, we're using the shortcut formula, so we're not done. Okay, now we need to plug in our means on here. So we have our 1.75 minus mu of x and mu of y, and this comes out to negative 0.02. Now we're almost done. We can turn this into a correlation using this formula, the covariance over the square root of the variance of x and the variance of y. So let's do that real quick. Plug in our numbers, and we'll see that our correlation is negative 0.0822. So we've actually found a theoretical correlation for this. Moving on. This example shows you how to put all the items together to obtain a theoretical result. Okay, we have a bunch of theoretical results there. And right now it seems very esoteric. It's like, why in the world are we doing this? But this is incredibly important later for statistical inference. And as a data science, we have to know that these rules exist, so we have some understanding of where the formula that we come up with, right? We're going to use a computer formula, or a computer that uses formulas, and we need to know where they come from and why they work. That doesn't mean you're going to have to do these on your own. It just means you should have some appreciation for where these come from. All right, so we're already running on 8 minutes, so we're going to jump into the next video, which is the bivariate normal distribution. See you there.